What if I told you that every electron you've ever seen, touched indirectly, or measured in a lab is not just similar, but literally the same kind of existence repeating itself across the entire universe, with no exceptions, no individuality, and no history that makes one different from another? Not almost identical, perfectly identical, every single time. The electron inside your body right now is indistinguishable from the electron in a dying star, or one created in a particle accelerator, or one that has been traveling through intergalactic space for billions of years. If you swapped them in any experiment, physics would not notice, not even in principle. So the question is not just, why are they similar? The real question is deeper. Why does nature refuse to give electrons any identity at all? To understand this, we have to start in a place that feels deceptively simple, almost boring. The atom. Everything you know, from chemistry to biology to the glow of distant galaxies, depends on electrons sitting around atomic nuclei. For a long time, scientists thought of electrons as tiny orbiting particles, like miniature planets circling a sun. That picture works for intuition, but it breaks immediately when you ask a sharper question. If electrons are little objects, then which electron is which? In classical thinking, objects carry identity. A marble has a history. You can track it, mark it, number it. But in the atomic world, that logic collapses. If you take two electrons inside an atom and exchange them, nothing measurable changes. Not energy, not structure, not outcome. The universe behaves exactly the same. That is already strange, but quantum mechanics pushes it further. Experiments show that electrons do not behave like distinguishable objects at all. Instead, their behavior depends on something more fundamental, the symmetry of their combined state. When you try to label electrons, nature simply ignores the labels. It treats them as if the labels never existed. This is not a philosophical choice. It is enforced by mathematics and confirmed by experiments. And here is where things begin to shift from weird to cosmic level strange. In modern physics, electrons are not considered tiny balls flying through space. That idea is replaced by something more radical. The electron is an excitation of a field that fills the entire universe. This is called the electron field. Imagine space itself, not as empty nothingness, but as a vast, invisible medium stretching everywhere, even between galaxies, even in regions where there is no matter. Now imagine that this medium has a specific mode, like a musical instrument that can only produce one type of vibration for electrons. Every electron you detect is not a separate object created from scratch. It is a localized ripple in the same underlying field. So when you ask, why are all electrons identical? Physics gives a surprisingly clean answer at this level. Because there is only one electron field in the universe. And every electron is just that field, excited in the same way, governed by the same rules. This already removes the idea of individuality, but it also raises a deeper tension. Why is there only one electron field? Why not slightly different versions scattered across reality? Why not electron A in one galaxy and electron B in another, with tiny variations? This is where the universe becomes more rigid than intuition expects. The standard model of particle physics, the best tested framework we have, does not allow arbitrary duplication of fundamental fields. Each type of particle corresponds to a specific field with fixed properties: mass, charge, and spin. For electrons, those properties are a fixed negative electric charge, a fixed mass of about 511 keV/c², a spin of 1/2.
These values are not assigned to individual electrons. They are properties of the field itself.
Every excitation inherits them automatically, like waves inheriting the nature of the ocean they form in. So an electron created in a laboratory today is not new in any meaningful sense. It is the same type of excitation that has existed since the early universe cooled enough for matter to form. And this leads to a surprising implication. If the electron field has always existed everywhere, then every electron is not just identical in properties, it is identical in definition. There is no hidden parameter that could differentiate one from another, no internal tag, no hidden memory, no identity code. At this point, even space-time distance becomes irrelevant to identity. Two electrons separated by billions of light years are not two individuals with matching traits. They are expressions of the same underlying entity type repeated across space. But quantum mechanics introduces an even stranger rule that reinforces this. When you have multiple electrons, their combined wave function must obey a property called antisymmetry. This is not optional. It is enforced by something deeper in quantum theory, linked to spin and statistics. What it means in simple terms is this. Swapping two electrons does not produce a new physical state. Instead, the mathematical description changes sign, but all observable consequences remain identical. So even at the level of equations, nature refuses to care about labeling electrons. This is why chemistry works the way it does. Electrons stack into atomic orbitals in very specific patterns, not because they are choosing positions like particles in space, but because the symmetry rules restrict what combinations are allowed. And this scales upward. It determines how atoms form. It determines how molecules bind. It determines how stars generate pressure against gravity. And ultimately, it influences the structure of galaxies. Because in stars, electrons are packed so tightly that quantum rules, especially the exclusion principle, create a kind of pressure that supports white dwarfs against collapse. Without the identical nature of electrons, stellar remnants would behave completely differently. Galaxies would evolve differently.
Even the distribution of elements across the cosmos would change. So something that begins as a statement about identity becomes a structural rule of the universe. But we still haven't touched the most uncomfortable part of the question. Why does reality choose this kind of simplicity? Why not allow variation among electrons? At the deepest level of current physics, there is no known mechanism that produces electron individuality. The Standard Model is built so that identity is not a variable. It is removed entirely from the system. In other words, the theory does not explain why electrons are identical in a causal sense. It is constructed in a way where non-identical electrons are not even definable. And that is where modern physics stops giving intuition-friendly answers and starts pointing towards something more abstract. The properties of particles may not be chosen by nature in the way we imagine choices. Instead, they may be fixed by underlying symmetries of the universe itself, rules so fundamental that breaking them would not just change physics, but make the concept of a particle inconsistent. Because once you push past the Standard Model description,
physics starts to suggest something more unsettling. What we call an electron is not an object that exists in space the way a grain of sand exists on a beach. It is closer to a persistent rule that space-time is constantly obeying. A useful way to move forward is to stop thinking in terms of particles entirely and think in terms of constraints. In quantum field theory, the universe is not built from little objects moving around. It is built from fields that cannot be turned off. Every point in space has a value for every field: electron field, quark fields, photon field, and what we call particles are stable disturbances in those fields. But here is the critical shift. The electron is not just a disturbance in the electron field. It is the only allowed stable disturbance of a certain kind in that field.
this is where identity dissolves. If you imagine a guitar string, you can create vibrations, but not every vibration is stable. Most patterns decay immediately. Only certain standing wave patterns survive. Now imagine a universe where only one type of standing wave is allowed for a given string, and every time that wave appears, it is identical in every measurable property. That is what the electron field is like. So the question, why are all electrons identical, starts to transform into, why does the electron field only permit one stable representation of itself? To answer that, physics points towards something even more fundamental than fields: symmetry. Symmetry in physics is not about visual beauty. It is about invariance. What remains unchanged when you transform a system? The electron exists because of a deep symmetry called a gauge symmetry, specifically tied to electromagnetism, U1 symmetry. This symmetry is not optional decoration.
It is the structural requirement that forces electric charge to exist in a conserved, identical way everywhere in the universe. If you demand that the laws of physics do not change when you rotate the phase of a quantum wave function locally, you are mathematically forced to introduce a field that carries force. This becomes electromagnetism. Now, here is the subtle but crucial point. Once this symmetry exists, it constrains what kinds of matter fields can exist consistently alongside it. The electron is not added to the universe like an ingredient in a recipe. It is the simplest possible non-trivial representation that is allowed under that symmetry structure. That means something radical. The electron is not arbitrary. It is mathematically enforced. And once something is mathematically enforced at that level, individuality becomes impossible, because individuality would require additional hidden structure, extra degrees of freedom that the symmetry does not permit. So if two electrons were not identical, one of two things would have to be true. Either the symmetry is broken in a way we have never observed, or there exists deeper structure beneath the electron field that differentiates them. Experiments strongly rule out both.
High-precision measurements of electron mass, charge, and magnetic moment have been tested to extraordinary accuracy. If electrons had internal differences, even unimaginably small ones, we would see deviations in atomic spectra, quantum electrodynamics predictions, and scattering experiments. We do not. The agreement between theory and experiment is so precise that the electron behaves as a perfect point-like excitation down to scales far smaller than any known structure. So now we are pushed into a sharper conclusion. Electrons are identical because the universe contains no physical parameter that could encode individuality at all. But this still feels incomplete because it is descriptive rather than explanatory. It tells us what happens, not why reality is built this way. To go further, we have to confront a more abstract idea that emerges in modern physics. Particle identity is not a property inside spacetime. It is a property of the underlying state space of the universe. In quantum theory, the true object is not the particle in space, but the wave function in Hilbert space. And in that space, identical particles are not labeled, because labeling is not physically meaningful. This is where the famous indistinguishability principle becomes more than a rule. It becomes a statement about ontology. If you try to assign identity labels to electrons, you are introducing structure that the mathematics immediately cancels out. Every observable quantity is invariant under permutation of identical particles. The universe is blind to the labels. This is not like forgetting names. It is more like the universe refusing to acknowledge that naming was ever a valid operation. Now extend this across the cosmos. An electron in a galaxy 10 billion light-years away is not another instance of a type. It is the same quantum entity type instantiated under the same global rules. Distance does not create differentiation because distance is a property inside spacetime, while identity here is not defined in spacetime at all.
This leads to a more extreme interpretation that some physicists are careful about but cannot fully dismiss philosophically. All electrons may be considered manifestations of a single underlying quantum field mode that is globally defined across the universe. Not one electron per place, not many electrons, but one electronness, repeatedly expressed wherever conditions allow.
This is where intuition starts to break, because we are used to thinking that multiplicity implies individuality. But in quantum field theory, multiplicity only means multiple excitations of the same underlying structure. The universe does not copy electrons. It reuses the same template without variation. And this reuse is enforced not by choice, but by consistency. If electrons were not identical, the mathematical structure of quantum electrodynamics would lose gauge invariance, probabilities would fail to conserve, and the theory would stop being predictive. In other words, non-identical electrons would not just change physics, they would break the internal consistency of the framework that makes physics work. So identity is not missing, it is prohibited. At this stage, we can push one level deeper still.
Why does the universe prefer such strict consistency at all? Why is reality built so that symmetry constraints eliminate individuality rather than allow it? Here, physics becomes silent in terms of mechanism and shifts into structural necessity. The working assumption is that the universe is not constructed from independently chosen rules, but from a single, consistent mathematical framework. Within such a framework, every allowable entity is not selected, but derived. Electrons exist because they are a required feature of a stable gauge-symmetric quantum theory that includes electromagnetism, relativity, and locality. Remove electrons, and the structure collapses. Alter them, and consistency breaks. So what we call electron identity is not a property waiting to be explained. It is a consequence of the universe refusing inconsistency. And now the implication begins to expand beyond particles. If electrons are identical because they are enforced by symmetry, then all fundamental particles may be similarly constrained. And if that is true, then the entire diversity of matter is not a collection of individually designed components, but a small set of necessary solutions to deep mathematical constraints. At this point, we are no longer asking about electrons alone. We are asking whether anything in the universe could have been different at all, and whether difference itself is something physics truly allows at the most fundamental level. Now we arrive at a point where even many physics graduates begin to feel uncomfortable, because the question is no longer about particles. It is about the nature of existence itself. The deeper you investigate identical electrons, the more you discover that the universe appears to be constructed in the opposite way from how human intuition expects. Human intuition starts with objects and then looks for patterns. Modern physics starts with patterns and discovers that objects emerge from them. This reversal changes everything. Imagine an alien civilization examining Earth from orbit without knowing anything about biology. They might notice billions of waves moving across oceans. At first, they could believe every wave is an independent object. Later, they would realize that waves are not fundamental. The ocean is fundamental. Waves are merely recurring excitations of a deeper medium. Quantum field theory makes an analogous claim. Electrons are not fundamental objects. The electron field is fundamental. Yet even this statement is not deep enough.
Because the electron field itself may not be fundamental. The Standard Model successfully describes known particles, But many physicists suspect it is not the final layer of reality. The fields we observe may emerge from something deeper, just as temperature emerges from molecules. If that is true, then identical electrons are not simply identical because of the electron field. They are identical because both the electron and the electron field emerge from an even deeper structure that only permits one electron-like possibility. This idea appears repeatedly across advanced theoretical physics. In quantum field theory, particles are classified through mathematical objects called representations of symmetry groups. This sounds technical, but the implication is profound. The electron is not defined primarily by what it is. It is defined by how it transforms. In other words, the universe identifies particles through relationships rather than substance. A particle is characterized by properties such as mass, spin, and charge because these determine how it behaves under space-time symmetries and gauge symmetries. Notice what is missing. There is no material from which an electron is made. There is no tiny internal core carrying a personal identity. There is only transformation behavior. This is astonishing. At the deepest successful level of modern physics, particles are not things. They are representations. They are mathematical patterns that remain consistent under specific symmetry operations. The electron exists because the universe allows a particular representation of the combined symmetry structure of spacetime and gauge fields. Identity comes from mathematics. Not matter, not location, not history. Mathematics. And once a particle is defined this way, individuality disappears automatically. You cannot have one electron secretly behaving differently because then it would belong to a different representation altogether. It would literally be a different particle. Now let's go even further. One of the most remarkable discoveries of 20th century physics is something called the spin statistics theorem. This theorem links two concepts that initially seem unrelated: spin and identity. Electrons possess spin 1/2. Because of this, they obey Fermi-Dirac statistics.
This means their wave functions must be anti-symmetric under exchange. The theorem is derived from a combination of quantum mechanics and special relativity. References: Wolfgang Pauli, 1940, Spin Statistics Theorem. Steven Weinberg, Quantum Theory of Fields, Volume 1. The astonishing part is that the theorem is not added manually. It emerges from demanding that relativity and quantum theory coexist consistently. If electrons were distinguishable individuals, much of this structure would collapse. The Pauli exclusion principle would disappear. Atomic structure would change completely. Matter itself would become unstable. Think about that carefully. The solidity of your chair, the existence of chemistry, the periodic table, the structure of stars, all depend on electrons being fundamentally indistinguishable. This means identicality is not a curiosity. It is one of the load-bearing pillars of reality. Now, zoom outward, far beyond Earth, far beyond the solar system, far beyond the Milky Way. Inside white dwarfs, gravity attempts to crush matter inward. Yet these stellar remnants resist collapse. Why? Electron degeneracy pressure. The exclusion principle prevents electrons from occupying identical quantum states. As gravity compresses matter further, electrons are forced into higher momentum states, generating pressure. No heat source is required. No chemical process is required. The pressure emerges purely from quantum identity. The fate of stars depends on electrons refusing individuality. A white dwarf is essentially a cosmic monument to quantum indistinguishability. References: Subramanian Chandrasekhar, 1931. Chandrasekhar limit. Now imagine a universe where electrons possessed tiny differences, even unimaginably small ones.
The exclusion principle would weaken. Degeneracy pressure would change. Stellar evolution would change. Heavy element production would change. Galactic evolution would change. Planets like Earth might never form. Life might never emerge. The large-scale universe is quietly built upon microscopic identity. This connection between the very small and the very large is one of the deepest themes in modern physics.
A property discovered in quantum mathematics determines the architecture of galaxies. But now we encounter a mystery that remains unresolved. Why does the electron have exactly its particular mass? Why not heavier? Why not lighter? The electron mass is approximately 9.109 times 10 to the negative 31 kilograms. In the Standard Model, this mass originates from interaction with the Higgs field. But the theory does not predict the value. It merely accepts it as an input parameter. References Standard Model Particle Data Group, Higgs mechanism. This creates a fascinating tension. We understand why all electrons share the same mass, but we do not understand why that mass is what it is. The universe appears to contain a single electron template, yet nobody knows why the template has those specific numbers. This is one of the great open questions, and it becomes even stranger when viewed cosmologically. Imagine rolling the history of the universe backward. Galaxies disappear. Stars disappear. Atoms disappear. Nuclei dissolve. Eventually, the universe becomes a hot plasma. Go earlier still. Within the first fractions of a second after the Big Bang, temperatures become so extreme that familiar particles lose their individuality. The distinction between electromagnetic and weak interactions disappears. The Higgs field no longer possesses its present value. The electron, as we know it, effectively becomes massless. This means there was a time when the modern electron did not exist in its familiar form. The underlying quantum field existed, the symmetry structure existed,
But the low-energy particle we call an electron had not yet emerged. That realization is extraordinary. The electron feels timeless, yet the recognizable electron is itself a product of cosmic evolution. Identity emerged from symmetry breaking. The universe cooled. The Higgs field settled into a non-zero vacuum state. Particles acquired mass. The electron became what we know today. In a sense, every electron in your body is carrying information about an event that occurred nearly 14 billion years ago. Its mass is a relic of the early universe. Its charge is a relic of deep gauge symmetry. Its existence is tied to conditions established moments after the Big Bang. And now we reach an idea so strange that it sounds almost philosophical. Physicist John Wheeler once encouraged thinking about whether particles are less like objects and more like recurring events. In that view, the electron is not a thing traveling through time. It is a pattern repeatedly appearing in spacetime. This inspired Wheeler and later physicists to explore radical possibilities. One famous speculation, sometimes associated with Wheeler and discussed by Richard Feynman, imagined that all electrons might actually be manifestations of a single electron, tracing an extraordinarily complicated path through spacetime. This idea is not accepted as physical reality. It fails in important ways. But its appeal reveals something important. The fact that physicists could even entertain such a proposal shows how complete electron identicality appears to be.
The universe gives us no evidence whatsoever that one electron possesses any individuality beyond another. Zero. Not a trace. No scars from history. No memory of origin. No personal characteristics. Nothing. At the deepest level accessible to experiment, every electron looks like a perfect copy of a universal blueprint. Yet, Perhaps copy is the wrong word. A copy implies an original. Physics has never found the original. What it finds instead is a single mathematical structure expressed throughout reality. And that leads us toward an even deeper question.
If electrons are ultimately representations of symmetry, and symmetries themselves may emerge from something more fundamental, then what is the substrate beneath the symmetries? What is the level of reality from which space-time, quantum fields, particles, and even mathematical identities themselves emerge? At the frontier of modern physics, something remarkable begins to happen. The question, why is every electron identical, starts to merge with another question that sounds completely different. Why does the universe have laws at all? For centuries, scientists searched for smaller and smaller building blocks of matter. Molecules were found beneath substances, atoms beneath molecules, electrons, quarks, and other particles beneath atoms. But every time we discovered a deeper layer, the focus shifted away from material substance and toward mathematical structure. The deeper we looked, the less reality resembled a collection of objects, and the more it resembled a collection of relationships. Today, many theoretical physicists suspect that information, symmetry, and geometry may be more fundamental than particles themselves. In several approaches to quantum gravity, particles are not viewed as permanent entities, but as emergent features arising from a deeper informational substrate. The electron might not be a fundamental thing at all. It may be what inevitably appears whenever reality organizes itself according to certain mathematical constraints. One clue comes from a profound fact that is often overlooked.
Every experiment ever performed suggests that an electron remains perfectly identical, regardless of where it exists. An electron in a laboratory on Earth behaves exactly like an electron inside a star on the opposite side of the Milky Way. More astonishingly, light arriving from galaxies billions of light years away indicates that the same physical laws operated there when the universe was much younger. The electron's charge appears unchanged. Its mass appears unchanged. The quantum rules governing it appear unchanged. This uniformity is extraordinary. The observable universe spans roughly 93 billion light-years in diameter, containing hundreds of billions of galaxies, each with hundreds of billions of stars. Yet everywhere we look, the electron follows the same script. It is as though the entire cosmos is running from a single set of instructions. This raises a subtle mystery. Information cannot travel faster than light. Large regions of the early universe were never in causal contact with one another. Yet when we examine distant cosmic structures, the laws appear synchronized with astonishing precision. The electron behaves identically in regions that were once separated by enormous distances. Why should reality possess such consistency? Modern cosmology partially addresses this through cosmic inflation, a period of extremely rapid expansion proposed to have occurred fractions of a second after the Big Bang. Inflation can explain why vast regions of space share common properties. Yet inflation itself does not explain why the electron field has exactly its particular structure. It merely spreads that structure across the cosmos. The deeper question remains untouched. Some physicists believe the answer may lie in deeper principles of consistency. In this view, the electron is not one possibility among many. The properties we observe could be less like arbitrary choices and more like unavoidable consequences. This idea appears repeatedly in advanced theoretical research. When physicists attempt to modify fundamental particles, they often encounter severe mathematical problems. Tiny changes can produce infinities that cannot be removed, violations of probability conservation, unstable vacuums, or contradictions with relativity. The universe seems remarkably intolerant of inconsistency. The electron survives every test because it fits into the mathematical architecture with extraordinary precision.
A related insight emerges from quantum information theory. Increasingly, physicists are discovering that information may play a deeper role than previously imagined. In black hole physics, thermodynamics, quantum entanglement, and holography, information appears repeatedly as a foundational concept. Some researchers have even proposed that spacetime itself may emerge from networks of quantum information. If this direction is correct, then particles may not be the foundation of reality. Instead, particles could be stable informational patterns embedded within a deeper quantum structure. The electron's identicality would then reflect the fact that the underlying informational code permits only one electron solution. The holographic principle pushes this possibility even further. Developed from studies of black holes by physicists including Gerard 't Hooft and Leonard Susskind, the principle suggests that the information content of a volume of space may actually be encoded on its boundary surface.
In certain formulations of quantum gravity, our familiar three-dimensional universe could emerge from deeper informational descriptions existing on lower dimensional boundaries. If space-time itself is emergent, then electrons are emerging inside an already emergent arena. The implications become almost dizzying. The electron field may emerge from a deeper theory. That deeper theory may emerge from informational relationships. Those informational relationships may generate space-time itself. And throughout every layer, the identicality of electrons survives. It is as if the universe is repeatedly telling us that individuality is not fundamental. Patterns are fundamental. This perspective also changes how we think about ourselves. Every atom in your body contains electrons that are completely interchangeable with electrons formed shortly after the birth of the cosmos. The electrons participating in your thoughts are not special versions of electrons. They carry no memory of Earth, no memory of biology, and no memory of their journey through cosmic history. They are the same entities that helped form ancient stars billions of years before the solar system existed. The iron in your blood was forged in stellar explosions. The carbon in your cells originated in stars. Yet the electrons associated with those atoms remain perfectly identical to every other electron in existence. The same quantum rules governing matter in distant galaxies govern the neurons firing in your brain at this very moment. This creates one of the most beautiful connections in science. The smallest known structures and the largest known structures are not separate stories. They are chapters of the same story. The identity of electrons influences atomic chemistry. Chemistry enables stars to synthesize elements. Stellar evolution shapes galaxies. Galaxies build the large-scale structure of the universe. And conscious beings eventually emerge capable of asking why electrons are identical in the first place.
The question therefore circles back on itself. A universe built from perfectly identical particles has generated minds capable of reflecting on that identicality. After more than a century of quantum theory, we can explain how electrons are identical. We can describe the mathematical symmetries that enforce their indistinguishability. We can calculate their behavior with extraordinary precision. We can trace their role from atoms to stars to galaxies. Yet the deepest mystery remains. Why does reality possess this particular mathematical structure rather than another? Why does the universe permit an electron field at all? Why do the underlying symmetries exist? And why do these symmetries generate a cosmos capable of complexity, life, and consciousness? Physics has not answered those questions. At its deepest frontier, the identical electron becomes a signpost pointing beyond current knowledge. What begins as a question about a tiny particle eventually leads to questions about symmetry, information, space-time, cosmology, and the origin of physical law itself.
And perhaps that is the most surprising discovery of all. The electron is one of the smallest things we know. Yet by asking why every electron is identical, we're led all the way to the edge of what humanity currently understands about reality.